Hello, my name is Keegan Lensink. I'm a junior programmer here at the Seismic Laboratory for Imaging and Modeling, and today I want to give you a quick demonstration of SeisIO.jl, which is a Julia package that I've been developing since August for getting seismic data into and out of the Julia environment. If you haven't heard of Julia before, Julia is a high-level, high-performance dynamic programming language for numerical computing. It's coming up quickly, it's getting popular, it's free and open source, so if you want to try any of this, you can go to julialang.org, download Julia, and give everything a shot for yourself. SeisIO has been made public on the Slim Group's GitHub page, so you can go to github.com/slimgroup/SeisIO.jl and take a look at the source code if you want, download it, run it, give everything a shot. There's some example data included in here, so you should be able to run everything that's in the README right out of the box. Well, SeisIO includes a performant reader and writer, and that may be all you want, but it's really quite a bit more than that. The package includes a parallel out-of-core scanner that reduces any number of SEGY files into a single out-of-core Julia object, and this object curates the file system for you so that you don't have to, providing direct and seamless access to subsets of the underlying data. But before we get into all that, I'd like to just quickly show you the reader and writer, so let's get started. What I'm going to show you today is actually a slightly modified version of the README, but it starts out exactly the same. So if you want to follow along and install SeisIO for yourself, all you have to use is Julia's package manager. So you see I already got Julia running, and you just need package.clone and then the GitHub link. If you have an account, use the top one. If you don't, use the bottom one. Again, this is all in the README. Starting out, reading a file with SeisIO is as simple as just passing the reader the file name. So first I'm going to go using SeisIO to expose all the methods at the top, so I can just say SEGY read is a function included in the package. So in this case I'd start out by just using SeisIO and then defining a file name, which is looking into the package directory and at one of the included data files. And then reading it is as easy as just running SEGY read and passing it the file. You'll note that the reader's warning that the fixed length trace flag is not set. You can see that in the block file header. That's true. It's not set. Even though it's warning you, it's because it's assuming that it is, and in this case it wasn't set, but it's going to continue anyway, reading it as if it was true. Right now SeisIO requires that it is true, but in the future that will change. So what you get back after a read is a size block, and this is a custom Julia type, which you can see includes the data as an array, the file header, and the trace headers. The file header contains metadata that's applicable to the entire file, so things that are constant throughout the file. Trace headers, you get one per trace in the data, and it includes information that's specific just to that one trace, so kind of things like receiver position and source position, and you get one of these per trace, but then the data itself is returned as an array so that it's easier to work on. So you can see here we loaded 3,300 traces, each with 751 samples. Most things are overloaded, so you can get the size of a block, do things like that. You'll notice that in this case, if we look at the file header, data sample format is 1, which is IBM float 32s. The package supports reading float 32s, but it is not a native Julia type, so there's not actually so much you can do with it right now. But I have included a conversion to IEE float 32s, which is data sample format 5. Default behavior is to go and read every single field in the headers, so even though these came out to be 0 in the read, it went and made sure and evaluated that, but you're given the option here not to do that if you don't want to. So perhaps you only want to know 4 of the fields, like source and receiver coordinates. You can specify those and the reader won't waste any time looking at anything else. So first I'm just going to define this little IO speed function, which is going to look at the file size and how long it took to read or write it, and then give you back in megabytes per second how fast the operation was. So I'm just going to repeat what happened above. I'm using elapsed so that this will evaluate only to the time it took to do, and I'm using the warning flag to turn off warnings. So we'll reread it, reading all the headers, and it read at 100 megabytes per second, and then running it again, only looking at source locations, and read at about a gigabyte a second, which is an order of magnitude improvement. A lot of this performance comes from the fact that we're doing everything in memory in an I/O buffer. You can turn that off by toggling the buffer keyword in the reader. So you can see here the function I'm calling is SEGY read on the same file name with the keys only on source X, source Y, and I'm turning off the buffer. So it's paging the disk for everything, which was about an order of magnitude loss in performance. So a lot of the performance you can get out of this comes from working in memory in a buffer, which is the default, and being able to specify a vector of keys for the fields that you want to read and not wasting time looking at anything else. And then of course, once everything's in memory in a block, there are methods for accessing and working with the metadata. Because the data itself is actually returned in an array, any Julia method that can work on an array is going to work on the data. You don't have to overload everything. But then returning a vector of headers, there's a getHeader function that goes and works through the vector of headers and grabs the field for you. So all you need to give it is the block and the header field that you want, and it'll go through and get that for every single trace and return it to you. And then if you want to write, there's the SEGY write function that's been included, and all you give it is a string, which is the destination path for the file it's going to write. It'll create it if it's not there, and the block, and it'll write the block for you. Right now, so I'll run it. IEEE float32s are supported for writing, not IBM float32s. So because the file I read was DSF1, which is IBM float32s, it's going to convert to IEEE float32s. Problem a lot of people run into is trying to save generated data. So if you'd like to save generated data, I've made that easy in SeisIO. So just as an example here, we'll make an empty array of zeros, which is sort of boring, but 1,000 samples, 100 traces. And then there's been an outer constructor provided so that you just pass a block, pass the size block method an array, and it'll automatically construct a size block for it and populate the headers with all the information it can find. So it detected our number of samples and our data sample format. And then there's in-place methods provided to go and update the headers. So for example here, if you wanted to go update the receiver positions, giving them a vector of receiver coordinates, it would go do that. So you can have variable metadata. And if you wanted to, you could pass it a constant. So if I just give it an integer or a constant, it'll apply that to every field in the block. Then we get to the third part of the package, the scanner that I mentioned at the start. And the scanner is designed to give you a multi-scale method of working with your data, meaning that it shouldn't matter whether you're working with 1 megabyte of data or 1 terabyte of data. You won't need to go rewrite how you're working with it based on the scale. So to do this, the scanner provides a direct method of accessing the data, meaning that it shouldn't matter whether you're working with one file that has 100,000 shots, and if you only want 5 of those shots, you shouldn't have to read the entire file to get a subset out of it. It's seamless, meaning that if you're dealing with directories with hundreds of files, you shouldn't need to go select files for loading based off the file name. You should be doing that based off the metadata, and it's performant. It's parallel, and it's out of core, meaning that there's no limit to how big the file can be. And as long as your file system can handle it, you can distribute it across workers and have multiple files being scanned at once. So this object that's returned is an out-of-core object. It doesn't contain the data. The data is left in disk in the original SEGY files. All it contains is a lookup table that it is built while it scans. You can specify pieces of the metadata you want it to look at. It's going to automatically detect shots, group them into partitions, and then it knows the byte locations of those partitions and which file for you, so that you say, I want the 10th shot in this data set, or I want shots that are in this certain source region, and that's all you need to tell the container, and it will go load that data for you. To demonstrate that it is actually multi-scale, we're going to perform this demonstration twice. Once on a small data set, it's 8 files, they're each 4.5 gigabytes, and I'm going to show you a little workflow, how to work with it, how to go access the data out of core. And then we're going to go do the same thing on a data set that's 14 terabytes, and you'll see that it's the exact same operations and there's almost no performance hit. So just to start, we're going to perform the actual scan. The scan is called with the SEGY scan function. You give it a directory or a vector of directories and a file filter. And this filter is going to go look at the files in those directory. If the file name contains this filter, it'll scan them. If not, it won't. And keys are looking up fields in the trace headers of the data, and it's going to give you a summary of each block it makes. So you can see here, I'm not specifying a block size that I want, and so that means that the scanner by default is going to go automatically detect shots. So it'll look through a big chunk of contiguous traces, look at the source locations, detect regions of constant source location, which means it's all traces from one shot, and partition the data based off that. So once we run this quickly, and we'll pass it also to that I/O speed we used before. So you see it scanned this file. It's a 4.5 gigabytes, did it in about 3 seconds, which is 1.5 gigs a second. So what we're left back with is S, which is this seismic container. And because we didn't specify a block size again, it's going to go automatically detect shots. So we can look at like the length of S. In this file, it detected 65 shots. And now we can access that. None of that data is in core, just the lookup table, which you see poorly displayed here. So if we wanted to say maybe find all the source coordinates, we can use get sources on the lookup table. And the lookup table, because it does already contain this information, it's not going out of core to get this. It already has this in core. But if we want, say, all the data for the first shot, what we can do is just index into the container, and it's going to go off core and actually read the data into a block, just as if we had used SEGY read. But we can make choices. So you can probably already see that you can set, you can sort these or set limits, find blocks in a region, and then you can call that. So say we ended up deciding we wanted these middle 20 shots, we can just go read those. And then this also, you can do this distributed. So in this case above, I scanned one file with one worker. Doesn't need to be like that. We can go over here. So this is a session I have set up where I have 8 workers, and we can go to the directory, back to the same directory, and we're going to look at all the files. So in this case, there's 8 files there, and we can scan them in parallel. So you see each worker is going to grab a file. It's sorted based on biggest files get scanned first so that the little ones can get done at the end. And I'm going to redefine our I/O speed over in this window, and we can see that when we scanned with 8 workers, we got a big performance gain. And now we have a container where we should have 8 times more shots. So yeah, in these 8 files, I detected 520 shots across all the files. And now that we're dealing with the container, if we want to load a part of file 2, we don't need to think about it in files anymore. Think about it in a data set. So we could just go load, like, what did we start on? We started on 65. We can go from 64 to 67. Now we just loaded data from shots from across a file, but you don't need to think of it like that. You just need to think of it as pieces of the data. So you can see that again here, from 65 to 66 in shots in this data set, we crossed a file boundary. And then if we ran timing on going out of core to read that, there's almost no performance hit. Yeah, it's exactly the same whether you're reading shots from the end of one file or crossing a file boundary into another. For the last part, I want to recreate kind of what I just did on that smaller data set on a much larger data set to show you that the exact same code and methods work. So there's some information about this last data set. This here is just a picture of the trace density. It's 13.3 terabytes 3D marine data. There's 155 files ranging from 1 gigabyte all the way up to 380 gigabytes. There's 200,000 shots and 1.5 billion traces. And the file names, I can't show them, but just looking at the directory, you would not be able to go do anything like this. You can't easily identify regions. So what I'm going to do here is go using SeisIO, which is the package I'm demonstrating. PyPlot is the plotting tools I'm going to use, and JLD is the Julia data type, so I'm loading something off core. This is what I had ran to scan it. So you see I collected source locations and receiver locations on all the files. It took 4 hours when I distributed over 8 workers, and the lookup table ended up being about 110 megabytes, which is pretty much a 10 to the 5 reduction in data size. So I'm not going to go scan it again because this video is not going to be 4 hours, and I think I have actually already loaded it, but because it's so small, this took 30 seconds to load, and you can see here when I check the size of what's in memory, my lookup table is only going to be 110 megabytes. So continuing, coming up to a big data set, we don't know anything about it. Because we've scanned for source locations, we can go get them all and get an idea of where all the sources are and plot them. So here we see kind of an acquisition where all the shots were fired. And then working with, well, all those source locations, we can start narrowing down what pieces of the data set we want to look at. So here I'm just going to define a little function in region. I'm going to give it the four corners of a box and then a coordinate location, and it's going to return either true or false whether or not those coordinates are within that box. So to define that, I just have a center and center X and a center Y, which is going to find the middle of the acquisition, which is all the source locations I just found when I scanned. I'm going to find a box that's going to end up being 200 meters wide and 200 meters tall, and then use the metadata to figure out the corners of that box. So we can do that quickly. And then what we can do is we can map this function to all the source locations that were automatically detected when we scanned it, and then this will come back and give us a list of all the blocks where shots were fired within 100 meters of the center of the acquisition. And then now we can plot this back onto the first picture we had, and we can see that when we zoom in, out of all those headers, we were able to identify that these block numbers are blocks where there's shots fired. And because we're working with the container, we can go directly access those. We don't need to think about what file they are or how big that file is. And what else we can do is we don't need to access all the data. We can do out-of-core metadata collection. So there's this read-con headers, which is an out-of-core way of skimming the file and collecting metadata for every single trace. When we scanned it, we didn't keep in the lookup table data from every single trace because that would get too large. We only took a summary of this block. So if we had one shot, it would tell you the biggest and the smallest receiver location in that shot, just to help you narrow it down. But if you want every single value for the trace, you need to use read-con headers or read the data itself. But because we don't want the data right now, we just want to look at the receiver position. So what I'm going to do now is collect the trace headers out of core. It's going to skim through all these blocks and collect all the receiver locations from shots that fired within that source region. And then it returns a vector of the trace headers just like it's in a block. I use get header again to go skim through those, and I get back a vector of receiver X and receiver Y. And now I can plot those. And in a separate figure, what I'm going to end up getting is an idea of where all my traces came from. So now we see we went out of core right there and read all the traces, all the metadata in, and I just wanted the trace headers. So when you look in the trace header, it only receives the receiver, and it automatically will detect elevation and receiver scalars when you get them back. So what you're looking at now is 4 shots fired in that little box. These are receiver locations, only for shots fired in that little box, and we just went out of core to get them. And of course, still I can go read the data out of core. So here I just want to read one of the shots that we've already narrowed down to within that region. So pretty quick, we're reading about 7,000 traces there. Pretty long traces too, 2,300 samples. And we're bringing it right into core, and you can work with it and do anything. It comes back in a size block. And so what else we can do there is we can work with this. Let's go load one of the shots. So I'm going to load one of the shots, and I'm going to take a look at it. So we just went off core into one file, no idea which file, doesn't really matter, and we can look at the shot record. And it looked weird, and that concerned me at first, but we have easy access to the headers, so we can try and get an idea of what's going on here. So we can take this shot, we can look at its receiver locations, put it back on the map, and realize that it's not hyperbolic because the data collection wasn't all perpendicular to the hyperbolic cone. We kind of collected along the intersection of this sweep and the hyperbolic cone, so it makes sense that it looks kind of weird. But if you didn't have easy access to go out of core and get the headers, that could scare you a little bit at first. And then finally, I just want to show you, because you're making decisions on what piece of the data set you want to load on the Julia objects, it can get arbitrarily complex. So we're sorting this sources, which is just an array of all the source locations. I don't need to think of it like a data set anymore. I can think of this just a vector of coordinate locations, and I can do anything I want with them. So we can get more complicated. I'm just going to define a function here, which is an in circle, I'm calling it. So instead of working with a box, I'm going to work with a center point, x naught and y naught, and then I'm going to find all the traces that are within a certain Euclidean distance of that point, so I can define a circle in a region. And we can combine those again. So now I'm going to define a first circle, and then offset it 1,000 meters diagonally, and say, but not in this circle. So I'm going to define kind of a crescent moon shape. And I mean, this might not be that practical, but it's just showing that anything you can do on a vector of locations, you can use that to define how you want to go load data. So we can go back to figure 1 now, go home, and see that in that last method, we sorted and went and collected data for shots that exist in this crescent moon of the acquisition grid. And then once again, that gave us another blocks vector. So these are all the shots that were inside that region that we constrained to, and just as easily I could go load some of the data. So we can load the first 4 shots out of there and bring that data in core. No problem. Well, that's all I have time to show you today. If you have any more questions, I encourage you to go over to the GitHub page. The README there is pretty fleshed out. There's some more technical information, and there's information about what you can do once you get a size block into memory. There's splitting, merging, tools to help you work with it. Thank you for listening. Once again, if you have any questions, send me an email at klensing@eoas.ubc.ca. Thanks.